Okay, so we're going to start by talking about adding some complexity, some reality into prey populations. So if you select the DD prey option, that gives you density dependence in the prey. And if you go ahead and select K equals 50, you should see something like this if you're looking at at N by P. So what you should be seeing here is that the predator isocline doesn't change at all. But what happens with the prey isocline is that as prey population sizes decline, it takes fewer predators to maintain their zero net growth. And that makes a lot of good sense, right? Why would you still need the same number of predators if your population density is declining? And so then you should see a green ellipse that looks kind of like this. And what this is referring to is the oscillations. And we talked a little bit about that in the last lecture. And you'll see that it's getting to a point. There's an attractor here. And what this is referring to is a stable equilibrium with damped oscillations. So now I want you to go ahead, I'm not going to draw it out, but go to the NMP by time, and what you should see is you should see these oscillations get smaller and smaller until we have a steady state. So go ahead and do that, change some of your parameters, see what happens if you change your parameters, and then we'll talk about what we need to do to make predators a little more realistic. Okay, so right now the model assumes that if you add one prey individual, then the predator efficiency increases linearly. And I told you that that's a type of functional response. The C to N was a linear functional response. And so that just looks like this. And there's multiple reasons why that's not the most accurate way to think about how predators will respond to increasing prey items. Now, excuse me. A more accurate way to model this response is what's called a type 2 response. This is a type 1 functional response curve for the predators. What's more common is you'll have an exponential increase up until its saturation point, and this is called a type 2 functional response. We see this quite often. This type 2 response is a more common response to prey availability. And there are a couple of things that contribute to this. One is that predators get satiated, so they don't constantly eat more and more prey. If they're full, they tend to stop eating. We can learn from them. The other thing that happens is we have what's called handling time. So the time spent searching for prey, the time spent actually capturing prey, even eating prey. This is all considered handling time. So we can look at handling time as a contributor to our models. So handling time, the total time to get a prey item is going to equal, so time is going to equal, it can be broken down into T of S plus T of H. So T of H is that handling time. So T of H is that handling time times the number of prey. And then we're going to have T of S, and that's going to equal N over A times capital N. So A is the per capita capture efficiency of the predator. And of course, N is the number of prey that they're eating, and capital N is the total number of prey that are in the habitat. And that means that we can rewrite this a little bit to say that feeding rate Okay, so feeding rate is going to equal N over T, which is going to equal the per capita capture efficiency of the predator times the total number of prey divided by this function that's looking at both the handling time and the capture efficiency of the predator times the population size of the prey. All right, so if you go back into Populus and click on type 2 in the model type box, so instead of having a functional response type 1 like we had before, you now have the saturating response. You should see some new terms. You can keep everything else the same, K equals 50, but change A to 0.2 and change T of H to 0.15. Okay, go ahead and do that, and I'll show you what it should look like. Okay, so you should see a graph that looks something like this. Okay, so if you go ahead and check and look at these over time, you should see a change in the way the oscillations look. And go ahead and do that and look at how those damped oscillations change and think about what it means to have it be more biologically reasonable. And then the last thing that I'm going to go over is I'm just going to tell you that there's a third type of functional response and show you what that looks like. So we've looked at type 1, which is linear. Looked at this type 1 functional response. We've looked instead at a type 2 functional response with a saturating curve. You'll sometimes see organisms have a type 3 saturating response, which is an S-shaped response. So you'll remember these from our logistic population growth models, where we have an inflection point. So we have this exponential growth until an inflection point, and then it flips to be a saturating response. So basically what that means is at low prey population densities, we're seeing predators eating as much as they come across. As prey population densities get higher, predators are satiated, prey are better at avoiding predators, and we see a flip to a slower predator efficiency. And you can look at that in Populus and change some of those parameters to see how a population growth model, a predator-prey dynamic model with a type 3 functional response occurs. This is actually less common than a type 2 functional response if we look at actual patterns in the wild in nature. But it is something that we do see happening sometimes, especially if we have a big difference between predator and prey population sizes at the starting point. Okay, so that's what we have for these Lotka-Volterra simple predator-prey models. We're going to spend class time, our synchronous class time, really looking at some behavioral traits of predators and also looking at food web models to understand how predation can affect the population dynamics of both predator and prey populations. And so I look forward to the discussion, and I will see you soon. Bye.